In this lecture, we define the notion of partial effects and average partial effects and apply them to Poisson regression. For a continuous regressor xj, we call the partial derivative of the conditional expectation function of y given x with respect to xj the partial effect of xj. For a discrete regressor, the partial effect is defined as the difference of the conditional expectation function evaluated at two different values of xj. In nonlinear models, unlike linear models, partial effects typically vary with x. The average partial effect is an attempt to give a single summary of all the partial effects by calculating the expected value of the partial effect over the distribution of x. Let's apply these definitions to the conditional mean model that we've been using for Poisson regression, namely the expectation of y given x equals e to the x prime beta. We calculate the partial effect as follows by differentiating and find that it's equal to e to the x prime beta times beta j. Notice that this partial effect varies depending on the value of x at which we evaluate it. However, because e to the x prime beta is always positive, the sign of the partial effect coincides exactly with that of the coefficient associated with xj. So the sign of the partial effect of xj is the same as the sign of beta j. To find the average partial effect, we simply compute the expected value of the partial effect over the distribution of x, yielding the following expression. We can estimate partial effects by simply substituting our maximum likelihood estimator beta hat, and average partial effects by doing the same thing, but then replacing the population expectation with a sample average over the observed values of x. Another way to summarize partial effects is to calculate their ratios. Relative effects are defined as the ratios of the partial effects for one regressor to those of another. Notice that for the Poisson regression model, partial effects will not depend on the value of x at which we evaluate them, because the e to the x prime beta will cancel out of the numerator and the denominator. On the problem set, you'll do a bit of work with average partial effects, and you will show that for the Poisson regression model, although this doesn't hold in general for all nonlinear models, the estimated average partial effect is equal to the sample mean of y multiplied by beta hat j. You'll also show that this implies that in order to compare the coefficients of a Poisson regression to the coefficients of an OLS regression carried out using the same data, we need to multiply by y bar to get the scale right.